Artificial variables are used in two forms. The first one is to account for a negative slack variable due to an inequality constraint that's a greater than or equal to, or for an equality constraint. As if h is equal to x1 plus 2x2 plus x3 is equal to 3, in the original tableau, what will happen is that x1, x2, and x3 are all assumed to be 0, which gives the equation that 0 must be equal to 3. Since this is not possible, we will need to add an artificial variable. In order to show this, I have an example where f is a nonlinear function. We're given an equality constraint and assuming that all your design variables must be greater than 0. We're given a start point and the fact that the move limits are plus or minus a half. The move limits are because we had a nonlinear function and we're limiting the space around the original point. You can do the math on your own, but the linearized function is x1 minus x2 plus 2 times x3 minus 1.25. That's the function you'll minimize. Now, from the fact that we have move limits, we have that x1, x2, and x3 are going to be less than or equal to a specific value. Only x1 and x3 are greater than or equal to a specific value because the lower limit on x2 is 0, which is a given in the matrix and therefore does not have to be stated by itself. So G1, G2, and G3, our x1 is less than or equal to 1.5, x2 is less than or equal to 1, and x3 is less than or equal to 1.5 respectively. Note that I group these together so that the slack variable numbering will work in the end. G4 is going to be x1 greater than or equal to a half, G5 is x3 greater than or equal to a half. And h is given as x1 plus 2x2 plus x3 is equal to 3. Now, if we want to write all these with slack variables, G1 turns into x1 plus x4 is equal to 1.5. G2 turns into x2 plus x5 is equal to 1. G3 is x3 plus x6 equal to 1.5. G4 is x1 minus x7 plus x9, where x9 is an artificial variable, and that's equal to 0.5. x3 minus x8 plus x10 equal to 0.5 is for G5, and again, x10 is an artificial variable. We also have the equality constraint, which gives us x1 plus 2x2 plus x3 plus x11 is equal to 3. x11 again is an artificial variable. So we need 3 w's. w1 is equal to x9, w2 is equal to x10, w3 is equal to x11. Put this into a tableau and you get x1 through x11 across the top is equal to b. G1 through G5 are the first 5 rows, then h, then f, and then the 3 w's. I have a line between f and w because I'm going to cheat. Instead of rewriting the matrix, I'm going to write w1, 2, and 3 over in canonical form right below it. In order to make this matrix canonical, we are going to have to subtract G4 from W1, G5 from W2, and H from W3. Note that H from W3 is to make it canonical, not because it actually has a negative number. But you can't say that W3 is equal to 0 initially. So once you do that, you get the last 3 rows. In this case, we now have x4, x5, x6, x9, x10, and x11 in the bases. All the other ones are out of the bases. Looking at W3, it has the greatest negative number at -2, so I'm actually going to pivot that one first. And if you look at the G's that I have available, there's only one G, G2, available to pivot around, so I've circled that one. It's also already a 1, so I don't have to manipulate it. This tableau shows the manipulations. I have eliminated all the zeros, so assume wherever there's a space, there's a 0. At the end of all the manipulations, your W3 row will still have a -1 in it. Notice it's both on x1 and x3. We're going to pivot around x1 though, and hopefully in the next iteration that will get rid of W3 and thereby x11. I have not actually finished this problem. You can do the iterations on an Excel sheet, and I will post a solution at some point.